In this video, we're going to do an introduction to geometric vectors. We'll start by looking at scalar versus vector quantities. Well, scalar quantities are quantities with magnitude only, whereas vector quantities are quantities with magnitude and direction. So a scalar quantity could be like distance, so the line at the grocery store is 400 meters long, whereas displacement could say the line at the grocery store extends 400 meters southeast of the entrance. So you've got both your magnitude and your direction there. Speed is another classic example. Speed is just the magnitude of the displacement over time, whereas velocity is displacement over time with a specific direction right there. Okay, speed again is only the magnitude, no direction. Okay, so there's a whole bunch of physical quantities here, and just take a look at these ones to determine which ones are vectors and which ones are scalars, and the answers are right here. We can also do geometric representations of vectors. We can represent a vector with a ray, which is a line segment with an arrow on the end, whose length is proportional to the magnitude and the magnitude of the quantity, and whose direction indicates the direction of the quantity. So, for example, vector AB, the vector starting at point A and ending at point B, could be represented as follows. This is our ray, this is our tail, and this is our tip or our head right here. So when we say vector AB, we classify this right here, the A, as being the tail, and B as being the tip. And so the tail is the start portion of the vector, and the finish portion of the vector is the tip. Represent these displacements on a vector diagram. So Cameron runs 10 meters north and then runs 5 meters west. Okay, so what we'll do is we'll use a ray, and so we'll go 10 meters north. Okay, and I'll label that right there. That's 10 meters. And then we're going to go 5 meters west. So if I'm going to go 5 meters west, what I should be doing here is I should make sure that the magnitude is approximately just like half the distance of the 10 meters. Okay, half the magnitude of this right here. So we'll say that that's 5 meters right there. Okay. Notation and describing length. Vectors can be labeled using their beginning and ending points, such as AB, or using a single lowercase, such as U, with the arrow on top. You may also see a bold letter U to represent a vector, or a half arrow above the vector, as you see written right here. The length of the ray is a positive real number, and that represents the magnitude of the vector. And we denote magnitude of the vector using absolute value notation. So if we just want to find the magnitude of how big a vector is, we can just put the absolute values around the vector sign. Common terms. Two vectors are equal if and only if their magnitude and direction are the same. Two vectors are opposite if they have the same magnitude but point in the same direction. So we can see here that A and B in this diagram have the same magnitude but point in opposite directions. You can also say right here that vector AB is equal to the negative of vector BA. And that's what we have over here as well. A, B, and BA are opposite. One is the negative of the other. BA is equal to negative AB and vice versa. Okay, so we have ABCDEF is a regular hexagon. Use correct notation to give examples of vectors which are equal, opposite, and equal in magnitude only. So some of the vectors that are equal here, we can say that like vector AB, which is going from A to B in this diagram, is equal to vector ED. Alternatively, FB. So FB is equal to EC. Right there. Vector FE is equal to vector BC. FE is equal to vector BC. Now, opposite vectors are just vectors that have the same magnitude but different directions. So an example of that would be FB is equal to negative CE, or you could also say that vector FA. Okay, so FA is equal to negative CD. Equal in magnitude, so just which ones have the same length, and we're not really looking at direction here. Okay, well, AB, if it's in a regular hexagon, then all the sides are the same. That magnitude is the same as the magnitude of BC. Okay. Similarly, the magnitude of CE is equal to the magnitude of BF. Okay, describing direction. The angle between two vectors is the angle formed when the vectors are placed tail to tail. That is, starting at the same point. So this right here, this theta, represents the angle between vector v and vector u. We can describe the angle between vectors in the following way. So if the angle between vector A and B is 45 degrees, well, then what we'll do right here is we'll have this as being A, and then we'll have this as being B. And yeah, I'd say that that's approximately 45 degrees. So we say right here, 45 degrees, okay, and this is vector A, and this is vector B. We can also describe the direction of a vector using north, south, east, and west. So A is a plane heading north 40 degrees west at a speed of 400 kilometers per hour. So here we go, we're going to go north and then 40 degrees west, or one of the other ways you can say this is 40 degrees west of north. So we'll say right there, that's about 40 degrees roughly. Okay, and there's my vector, and we'll say that that is 400 kilometers per hour. And I know that this right here is 40 degrees west of north. We can also use polar coordinates as well. A vector can be drawn from the origin of a 2D plane using polar coordinates, r and psi right here. How is A represented? Sorry, just a quick correction. This right here is actually pronounced phi. Okay, so how is A represented? So how would we represent this right here? Well, we would just basically do the exact same thing. We'd have our coordinates, okay? And then we're going to put our terminal arm here. And this right here, this R represents 400, okay? And then this right here would be 90 degrees plus your 40. So this one would be represented 400. And then you would say 400 and comma 130 right there. So I'll put 130 right there. Okay, so that right there is polar coordinates. Okay, finally we're going to take a look at scalar multiples of vectors. So for any vector v, negative v has the same magnitude as v but is in the opposite direction. 2v has the same direction but is twice the magnitude. And negative 3v has 3 times the magnitude as v and is in the opposite direction. Vectors which have the same or opposite directions are said to be parallel or collinear. For vectors to be parallel, one must be a non-zero multiple of the other. The zero vector is a vector of magnitude 0 and undefined direction, and we note it as 0 with the arrow on top of it. A unit vector is a vector of magnitude 1. If a vector is multiplied by a scalar 1 over the absolute value of that vector, then the result is a unit vector with the same direction v, and it's written v with a little hat on it, or v hat or v cap. This procedure is called normalizing v. All right, so this is our equation for normalizing v. So vector u has its magnitude as being 10 determine u hat. So u hat would just then be 1 over 10 times the vector. Right? So if this magnitude is 10, and then we multiply it by a tenth, then the magnitude will be reduced to 1. It preserves the direction, so we have u cap, or u hat. Okay, final activity here. Okay, so if b is equal to 2a, then I'm going to do a is right here, and then I'll do double that right there. So we've got 3 spaces, 4, 5, 6. Okay, and let's try and make this as straight as possible. right there. So that's going to be our B. Double the size of A. Okay, C is negative 2/3 of A. So A, I could take A and reduce it by a third, so that would just make it its unit vector, and then I'll multiply it by 2, so I'll end up over here, and then I've got to flip the direction because there's a negative in front, so I end up with this right here. Okay, and that is vector C. D, which is equal to A, okay, that's not so bad. We just make it, literally, we just insert a vector that is the same as A. Okay, and that's your vector D. E, which is opposite to A, so basically this same vector, and I'm going to copy and paste it. I'm going to put it right over here, and then I'm literally just going to flip it. There we go. Okay, and that's my vector E. It's opposite to A. And F, which is parallel to A. Well, if F is parallel to A, then the magnitude doesn't really matter, so long as the direction is the same. So I'll just make this right here, F. Again, magnitude doesn't matter here, so long as it is in the same direction. And then A hat is just the unit vector with the same direction as A. So there we go, just the unit vector right there. And then I'm going to write A hat. Okay. All right, so this is the first lesson of vectors, and yeah, thanks for watching.